Welcome to G Fun Facts Online. Today, we're venturing to the very edge of science and technology, to a field that is blurring the line between mind and machine. We're talking about neuroengineering and the incredible quest to build artificial neurons that think, learn, and remember, just like the ones in your own head. So, what exactly is an artificial neuron? To understand that, let's look at the real thing. A biological neuron is a tiny information processor. It gets signals from its neighbors, adds them up, and if the total signal is strong enough, it fires its own pulse of electricity to communicate with other neurons. It's this network of trillions of connections, strengthening and weakening over time, that creates learning, memory, and consciousness. The first attempts to copy this were purely mathematical. Back in 1943, the McCulloch-Pitts neuron was basically a simple on or off switch. Then, in the 1950s, Frank Rosenblatt's perceptron came along. This was a step up. It could actually learn from data by adjusting the importance, or weight, of its inputs to get closer to the right answer. But it was still very limited. The real breakthrough came in the 1980s with multi-layered neural networks and a clever algorithm called backpropagation. Think of backpropagation as a network learning from its mistakes. It calculates how wrong its final answer was and sends that error message backward through the entire network, telling each artificial neuron how to adjust its connections to do better next time. This is the fundamental process that powers almost all the AI you see today, from your phone's photo app to complex medical diagnostic tools. But even these powerful software models are just an abstraction. The real frontier, the field of neuromorphic engineering, is about building physical hardware that mimics the brain's architecture. The goal is to create a brain on a chip that is thousands of times more energy efficient than traditional computers for certain tasks. And the superstar component making this possible is the memristor. A memristor, or memory resistor, is a tiny electronic part whose resistance changes based on the electricity that has flowed through it in the past. It remembers. This makes it an almost perfect stand-in for a biological synapse. By zapping it with electrical pulses, you can gradually increase or decrease its resistance, which is the physical equivalent of a memory getting stronger or weaker. Engineers at MIT have already used this idea to build a chip smaller than a piece of confetti, packed with tens of thousands of these memristors that can remember and reproduce images with stunning clarity. They're not just using silicon either. Researchers are experimenting with all sorts of exotic materials. One of the most promising is phase change material, the same stuff used in rewritable DVDs. This material can be switched between a messy, high-resistance state and an orderly, low-resistance state. This is perfect for mimicking one of the brain's most important learning rules, spike timing dependent plasticity, or STDP. STDP is the brain's fire-together, wire-together rule. If one neuron fires just before another, the connection between them gets stronger. If it fires just after, the connection gets weaker. Timing is everything. Using phase change materials, scientists can create an artificial synapse that strengthens or weakens based on the precise timing of electrical spikes, using incredibly small amounts of energy. This brings us to the next generation of artificial brains, spiking neural networks, or SNNs. Unlike current AI that processes continuous numbers, SNNs communicate in the brain's native language, discrete spikes of electricity. They only do work when a spike occurs, making them incredibly power efficient. They can also encode information in the timing and patterns of these spikes, allowing for a much richer and faster way to represent the world, much closer to how your brain actually works. So we have the theory and we have the materials. But what can we actually do with this technology? The applications are already moving from the lab to our lives, and they are nothing short of world-changing. Let's start with medicine. For someone who has lost a limb, neuroprosthetics are offering a new reality. By implanting electrodes into the nerves of the residual limb, a person can control a robotic arm with their thoughts. But it's a two-way street. The prosthesis is also fitted with sensors that send signals back to the brain, allowing the user to feel the texture and pressure of an object they're holding. It's the difference between using a tool and having your hand back. Then there are brain-computer interfaces, or BCIs. You've probably heard of companies like Neuralink, which recently implanted its device in a human patient, allowing him to control a computer mouse just by thinking. Another company, Synchron, is using a less invasive method, threading its device through blood vessels to sit on the brain. Their patient was able to control an Apple Vision Pro. For people with severe paralysis from conditions like ALS, these devices are a lifeline, breaking them out of a locked-in state and allowing them to communicate and interact with the world again. This technology also holds immense promise for treating neurological disorders. For conditions like heart failure, where specific neurons in the brain aren't sending the right signals, a tiny implantable artificial neuron could one day restore proper function. For diseases like Parkinson's, deep brain stimulation is already used to quell tremors, and new closed-loop systems are being developed that listen to the brain's activity and adjust the stimulation in real time for more personalized treatment. Beyond direct brain interfaces, we're building neuromorphic computer chips. These chips, modeled on the brain's architecture with physical artificial neurons and synapses, are incredibly fast and efficient at the kinds of tasks the brain excels at, like recognizing patterns. This is a game changer for robotics, allowing a robot to learn and make decisions in real time, and for putting powerful AI into small devices like your smartphone or IoT sensors without draining the battery. Of course, this incredible power comes with a heavy dose of responsibility. We are wading into some very deep ethical waters. If a device can alter your brain's function, what does that mean for your sense of identity and free will? Who is responsible for the actions taken by someone using a BCI? Is it the user, the device, or the algorithm? The data from our brains is the most personal, intimate data that exists. The threat of brain hacking or unauthorized access to our thoughts is no longer just a movie plot. It's a future we have to plan for. And what about fairness? These technologies will be expensive. Will they create a new divide in society between those who can afford to repair or even enhance their cognitive abilities and those who can't? These are urgent questions we need to start discussing now. Despite these challenges, the path forward is exhilarating. We are at the very beginning of an era where the boundary between biology and technology is dissolving. The artificial neurons being meticulously designed in labs today are the seeds of a future where paralysis can be overcome, where degenerative brain diseases can be stopped, and where a new class of intelligent machines can help us solve humanity's greatest challenges. We are learning to engineer the mind, and in doing so, we are embarking on the ultimate journey of self-discovery.